going to start recording here. Okay. So, you know, we factor numbers. 6 equals 2 times 3. Well, we can factor matrices also. We can write a matrix A as a product of L times U. And there's more to this problem, so I'm going to let you copy this down. Okay. Yes, we will get to that, Solomon. What do L and U stand for? That is a very good question. Section 2.5, matrix factorizations. Got to get this right. Hold on, I want to just get it adjusted right. Okay. So, okay. So right now we're taking it on faith that the matrix A has this following factorization. L times U. And what do we notice above the diagonal here? Lower and upper, that's right, Sega. L is what's called a lower matrix. It's a lower triangular matrix because all the zeros, well, there are zeros above the diagonal. So the one, you got ones along this diagonal, and above the ones are zeros, and below the ones are non-zero entries, or at least they're not all zeros. So we call that kind of matrix a lower matrix. A lower matrix. On the other hand, for the other matrix, the second matrix, we have a diagonal here, 3, negative 2, 1. And below the diagonal are all zeros. And above the diagonal, we have non-zero entries, or at least they're not all zero. So that's called an upper matrix. So we usually call them lower triangular and upper triangular matrices. But you know, this second matrix, you know, lower triangular, upper triangular matrices, what form is this second matrix in? Isn't this second matrix here the upper triangular matrix? Isn't it in a special form? Ah, that's right. No, and Solomon, it's an echelon form. Okay, all right, and take it, believe me, the matrix A can be written as the product of this lower unit triangular matrix and this upper triangular matrix. So we have a lower triangular matrix times an upper triangular matrix. And actually, the matrix on the left, we call it a lower unit triangular matrix because there are ones along the diagonal. Now, the matrix A has this factorization. So here's what we want to do. we want to use this LU factorization to solve the system AX equals B, where the vector B has the values -7, 5, and 2. Okay, give you a moment to copy that. Okay, so you're used to solving, you're used to saying, okay, if AX equals B, we can just solve this system. We can solve this system of equations using row operations. And we learn that if A is an invertible matrix, if it's a square matrix, we could let X equal A inverse times B. But that only works if A is a square matrix, by the way. The row operation approach, getting the matrix in reduced, the augmented matrix, getting it in reduced echelon form, is that universally works, because A doesn't have to be a square matrix always, but in this case it is. But nevertheless, okay. So how are we going to do this? Well, there must be a reason for using this LU factorization to solve the system AX equals B. There must be a reason for this. All right, let me show you how this works. Okay, so for our solution, we have A times X equals B, but I know that A can be written as L times U. So A times X equals B is the same as LU times X equals B, for sure. Okay. And but we remember that matrix multiplication is associative. So L times U times X, well, I can write that as L times U times X equals B. And what I'm going to do is I'm going to define U times X to be that's going to be a vector. That's going to be a vector, right? It's going to be a vector with variables. Well, it's going to be a vector. It's going to be it's going to be a vector where the entries have variables in them. Okay. I'm going to call that variable vector Y. So if Y equals U times X, then this here can be thought of as L times Y equals B. That's the matrix equation. And I want to solve that for Y. I want to solve that for Y. So, of course, I'm going to solve this augmented matrix. And here's the augmented matrix. Now, looking at this augmented matrix here, does it look like a hard matrix to solve, to do row operations on? Does it look difficult or easy? No, it looks easy. Thank you, everybody. Why? What makes it easy? Why is it easy? And why are there few operations, Sega? Why? Why is that? But what cuts down on the number row operations? We have the ones, we have pivot ones, okay, but there's something else. The zeros. That's right. That's right. We have zeros here, right? So that's gonna, I mean, we want to get this in reduced echelon form. The zeros make it easy. So, okay. Well, okay, so I want to get, of course, zeros in this spot here, where the -1 is in the first column and where the 2 is in the first column. So I'll take 1 times row 1, add it to row 2, and replace the row 2 with that result. Well, Matthew, in this case, you're given the factorization, but in some cases, you're going to have to find the factorization, and that's what I'm going to show you next. I'm going to show you how to find that factorization. We also did -2 times row 1 and added that to row 3. Okay, I'm trying to be very neat with the mouse. I think this is neat. I think this is fine. Okay. And then finally, I need a -5 to be a 0. So I'll take 5 times the second row and add it to the third row and place the third row with that result. And we note that this is easy to do. Few row operations. Very few row operations. Okay, so we have solved for the vector y. But I want to make sure everybody's caught up here. All right. Are there any questions up to this stage? We're good? I can move to the next page. All right. So now we know that the vector y, thank you everyone, is -7, -2, and 6. Okay, that's going to be our, I mean, those are our answers for the vector y. But remember, if we go back here, we had let the vector y equal u times x, and we want to solve for x. X has our original variables, x1, x2, x3, so we want to solve for x. But now I found out what y is. I know what y is. So since y, whoops, hold on. Since the vector y is -7, -2, and 6, I'm going to solve the system u x equals y. I'm going to solve it for x. Okay, so this here, hold on. You know, what we have here is U Y. Equals, right? And incidentally, class, I know you're copying, but let me just add one thing to the previous page. Hold on. Here, let's add in our notes. Let's add in LB equals. Okay, just because, you know, it's true, right? So we'll add that in. And now, let's continue here. Okay, so this is does this augmented matrix seem like it's going to be easy to solve? It does. And why is that? Why is that, everybody? Well, it's already in echelon form, and you have these zeros at the bottom. So again, that makes our life easy. So in this case, what I do is I multiply the third row by -1, the third equation by -1, and then that'll be my new equation. That's third negative times the third row. Put the result in the third row. -1, really. I like to write it. Let me. Okay, and now I have a pivot. I have a pivot 1 in the third row, and that's going to allow me to get zeros where the -2 and the -1 are in that third column. So of course, I'll take I'll take 1 times the third row. That's right. Thank you, Solomon. And add it to row 2. And replace the second row by that result. And then, thank you, Solomon. I'm going to take, Solomon, repeat that again. I mean, I know what I'm doing, but thank you. 2 times row 3 plus row 2, or row 1, and replace row 1 with that result. Okay, and then now all we have left, well, I want to multiply the second row by negative a half. Thank you, Solomon. And then that goes in the second row. Okay, so I'm getting better with the mouse. I'm getting better. Okay, and then we'll move on. Finally, we got this negative 7 here. So that we got to make that a 0. So we'll use the 1 as a pivot. And I agree, of course, Solomon's right. 7 times row 2 plus added to row 3 and replace the row 3 with that result. May I go to the next page? Okay, thank you, everyone. Okay, finally, we did 7 times row 2, added that to row 3. Row 1, sorry, row 1. Yeah. And then hold on here, one moment. Okay, and then that result goes in row 1. And then I just wanted to then, you know what I do here, the last step. I take 1/3 times row 1. And that is going to be my row 1. Easy. So now your solution for x. Now you have your solution for x. Okay, how many kind of like this? Think this is kind of cool? Yeah. I agree. Thank you. Let me see, come back here. Hold on. Thank you, Christy, Solomon, Kevin. Yeah. Sega. And I'll point something else out, but I want to make sure everybody has this copy before I move. I want to point something out in the book. Well, actually, I won't point that out. Maybe yet. But the point is, you see, we have to think about solving very large systems of equations. And to solve very large systems of equations, we use computers, and computers have programs behind them. And if you have like a 1,000,000 by 1,000,000 matrix, if you have 1,000,000 variables, it could take a very long time for the computer to solve. And like finding an inverse for a square matrix that has 1,000,000 rows and 1,000,000 columns can take a very long time, and it may even be impossible. Depending on the memory and all that, and you got round off error. So mathematicians and computer scientists want ways to solve these huge systems of equations. They want to have other ways that are easier for the computer. So you know, it takes less blocks, less mathematical operations if your matrix has zeros in it. So basically, we did, using this LU factorization approach, we had to solve two systems of equations to solve eventually for our variables x, but it wasn't too hard to do. And if it isn't too hard for a human to do, hopefully it shouldn't be too hard for a computer to do. You see what I'm trying to say? You could program this in a computer, this algorithm. And in fact, you know, one of our MATLAB assignments is going to deal with LU factorization. MATLAB assignments, I'm going to start getting those ready this weekend, and I'll have you know, I'll get some posted, and I'm going to allow you to work together on your MATLAB assignments in groups, by the way. How large can the groups be? Maybe, you know, I'll have to think about that. But I think computer projects, it's good to work together on them. I think you learn from each other. So, but next week, that's next week. Okay, any questions on this before we move on? Okay, so you're required to solve for the vector y first. That's right. That's right, Sega. This is how you would do it. But the question comes then, how do we get this factorization? I mean, in the beginning, we were told that that the matrix A factored into this, had this LU factorization. Well, we need to be able to find the LU factorization. And to find that, there is a procedure. There is a procedure, and I guess what I want to show you is the following here. Let me bring it in the from the book here. Share application. Yeah, let me bring the book up. Okay, so this here is the LU factorization algorithm. Okay, and this is just represented symbolically. But what it's saying is, if you have a, you know, the matrix A, we're supposing it can be reduced to echelon form. Okay, and that's a pretty, you know, I mean, pretty good assumption there, right? But we're assuming it can be replaced using only what are called row replacements that add a multiple of one row to another row below it. In other words, this is a restricted version of an LU factorization. Now, you're going to learn a more general version in one of the MATLAB assignments. But for now, what you're doing is to take a matrix A and row reduce it to a matrix in echelon form requires row operations. We know from the last class that these row operations can be represented by multiplying the matrix A times these elementary matrices. We know that, okay? And in fact, the elementary matrices that are going to convert or reduce the matrix A to echelon form, upper echelon form U, are going to be unit lower triangular matrices. Okay, they're going to be unit lower triangular matrices. And if you need to see this, I have actually something I worked out. It isn't something I necessarily want you to copy now, okay? But let me at least bring it up, and it'll be on the recording. So what I've done here, is I want to justify what they're talking about. That in the book was statement 3 in section 2.5 on page 127. You know, that if you take the matrix A and pre-multiply it by a set of elementary matrices that are unit lower triangular, okay, if you do that, then you'll produce the matrix A will be in echelon form, upper echelon form. Well, echelon form, the form of an echelon matrix is it's an upper matrix because all the zeros are below the diagonal. And what I'm showing here is I have this matrix A. I guess you can copy it if you want, you know. This is to justify the statement. It's an example. Again, when I see, you know, math and it's a little bit abstract to me, I try to justify it using an example. So here's a matrix A. 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, I didn't use 9, I used 10. And what I'm doing is I'm pre-multiplying the matrix A by 3 unit lower elementary matrices. E1, E2, and E3. Let me let you copy this down first. Okay, and then we'll continue. Okay, so now we're going to continue here. I did have one question for a student. Nothing bad, nothing bad. Matthew Uberall, Matthew, I had a question for you. I wanted to ask after class when class ends. Nothing bad. It's just a question. Can you stay after class for a moment? All right. So I'm asking Matthew. Thank you. All right. Actually, maybe we'll have 2 students. I don't want this. Isn't bad. This isn't bad at all. Hold on. I need to test something in my math lab, and I need a couple of students to help me test it. It's for class. Yes. Let me see. Vivian, can you stay after class just for a moment, too? Vivian and Matthew, I need to test something in my math lab, and I need a couple of. It'll only take like a minute, but I need 2 students to help me. Would you be willing, Vivian? And it only take a minute because I know, you know, you're getting your work together for the exam and all that. But all right, well, I only need 1, but we'll get Vivian next. Okay, so very good, very good. And class, once again, there's nothing bad about this. I need to test something in my math lab, and I need a student to help me with it. That's why I'm asking. So maybe if a couple more of you would be willing to stay after class, I would appreciate it. Okay. All right. Let me see here. So, okay. So you see what I'm doing is I have 3 elementary matrices. They are lower triangular because the zeros, you notice above the diagonal, there are zeros. And they're unit lower triangular because the diagonal itself has 1s along the diagonal. Okay, and they're elementary matrices because an elementary matrix is when you do a row operation on an identity matrix. So like the E1 matrix, what I did was I took the identity matrix and added -4 times the first row to the second row, and then replaced the second row with that. What I'm showing here is that by pre-multiplying the matrix A by these 3 unit lower triangular elementary matrices, I'm able to get the matrix A in upper form, in upper echelon form, or echelon form, but we call that U. Okay, so and so now what we're going to do is we're going to look at the LU factorization algorithm from section 2.5, and then an example that shows that in the text. So what you're learning here is that you can take a matrix A and by multiplying it by a series of lower unit triangular matrices, that's going to reduce the matrix A to a matrix in echelon form. That's what you're learning here. Okay, are there any questions before we move on? All right. All right, so what I want to do is I want to bring up the book. May I go to the book now? Are we, has everybody had a chance to copy this? Or does somebody, do you want to, do you need a little more time? Thank you, Matthew. Thank you, Kevin. Thank you, Christy. Okay, perfect. Okay, so now I'll go to the book. We appreciate now the statement in the book that we saw. We appreciate now this statement 3. Now we understand that it makes sense. But of course, the matrix A, if we want to get the matrix A by itself, we multiply the matrix A will equal then, if you multiply by the product, the inverse of the product of these unit lower triangular elementary matrices, if you multiply by the inverse of the product, the matrix A then is going to equal that inverse of the product times U, and that's going to be L times U. So the product of these lower, the product of these lower unit triangular matrices is going to be a lower unit triangular matrix. Okay, and the inverse of that will be a lower unit triangular matrix because you're happy, well, yes. So okay, so this means then that the lower unit triangular matrix can be represented by the inverse of the product of these elementary matrices. Now, the key, this is really, I'm going to the next page. Why is this important? Why is this important? Because here's sort of the key sentence. The row operations which reduce the matrix A to U in echelon form U also reduce the matrix L to the identity matrix, because the product of the elementary matrices EP to E1 times L, okay, is going to convert L to the identity matrix, because L can be represented as the inverse of the product of those elementary matrices. So we're looking to find the echelon form of the matrix A, but while we do that, we're also at the same time going to find the lower unit matrix, okay, that we need. So we reduce A to echelon form. The algorithm is reduce A to echelon form by row replacement operations if possible, which we'll do. And then we're going to place the entries in L such that the same sequence of row operations L reduces to I. And this is where example 2 comes in. So to appreciate this algorithm, to understand it, I had to show you that example that I did. Find an LU factorization. Find an LU factorization of A. Now A here is a 4 rows, 5 columns. You don't have to have a square matrix to find an LU factorization. So what they do is this. They're going to reduce the matrix A into echelon form. They're going to reduce the matrix A into echelon form. The row operations that create zeros in the first column of A will also create zeros in the first column of L. So what they do here is, in the matrix A here, okay, hold on. They do row operations to produce zeros. Can't quite get that. I don't want it. Hold on. I didn't want that to. Hold on. Can I erase all this? How do I erase all this? Is it possible? Well, it's no big deal. It's no big deal. So they did some row operations, and they took this pivot 2 here. I don't know, man. Hold on. Hold on. Trying to think how to erase this. It's okay. It's all right. They do row operations, okay, to produce. If we look here at the A1, okay, in this statement 5 here, something else I'll learn here. They did row operations, and it produced zeros in the first column of A. They used well, yeah. So they multiplied the first row by 2 and added that to the second row. They multiplied the first row by -1 and added that to the third row. They multiplied the first row by 3 and added that to the third row. Okay, so we just see here. Hold on. Now what they do then is, if we go to the next page, okay, what they do is they take the first column and they divide all the entries by, I want to say this the right way, by 2. Okay, because dividing the top entry by oh, I just figured out how to do it. Okay, dividing the top entry by 2 makes it a 1, but then you have to divide all the other entries by 2. Now, this is just an algorithm for finding the lower unit triangular matrix L. It's an algorithm. Okay, I'm not saying these are legitimate, like you're not doing a row operation here by dividing the first column by 2. It's not a row operation. You're getting a 1 along that diagonal, and you'll notice that 2 times 1 added to the second row gives you 0. -1 times 1 added to the third row gives you a 0. And 3 times 1 added to the third row gives you a 0. So the same row operations that produced the same row operations that got the first column of the matrix A in echelon form, that portion, are the same row operations that's going to get the first column of the matrix L to the identity matrix. And so that's what we're doing. If we go back here, okay, if we go back, look here at now the second column. You have a 3, a -9, and a 12. Okay, so to produce the second column of the lower unit triangular matrix, what are you gonna do? What are you gonna divide by? You're gonna divide by 3, and that produces the second column of the lower unit triangular matrix. And notice 3 times, well, hold on here. 3 times 1 added to the third row, 3 times 1 added to -3 is 0. -4 times 1 added to -4 is 0. Well, those same row operations are going to get us closer to echelon form. 3 times 3 added to the third row is 0. -4 times 3 added to the fourth row is 0. That produces then the A2 matrix, and you're closer to echelon form. So do you see what you're doing is you're doing the simultaneous row operations that you're doing to get the matrix A to echelon form will also be the same row operations that will cause the matrix L to be in, that will reduce the matrix L to the identity. But because L is a unit triangular matrix, you have to divide each column by the appropriate number so that you get 1s along the diagonal. That's what I'm trying to say. And I think you're going to have to just look at this example perhaps again, and then of course there'll be help me solve this help aids for section 2.5. But that's the idea, and it's something that, let me stop the recording.